Hello everyone, I'm Siddhi Brahmbhatt and today I'm going to talk about my work on creation of a dataset and model for crossing Indian roads. This work was done by me as a final year student at G.H. Patel College of Engineering and Technology. In simple words, this is a project to aid blind people cross busy Indian roads. We all know that our roads have lots of traffic and sometimes don't have well-defined traffic stops and crosswalks. This makes it difficult for the blind people to cross roads, as vision is crucial in determining the road crossing safety. In this paper, I propose a variable assistant that runs a pre-trained classifier model to predict road crossing safety from a real-time video stream. Getting into the technical details, my work was roughly divided into three phases. I think that reliable safety classifiers have the potential to help the blind cross Indian roads, but to the best of my knowledge, there is no existing dataset collected on Indian roads from a pedestrian viewpoint, which is labeled for road crossing safety information. Hence, I introduce INDRA, Indian Dataset for Road Crossing, the first dataset of this kind. Next, I also present an analysis of rigorous training experiments performed to develop a road crossing safety classifier. Further, I also present a low-cost and feasible working prototype of road crossing assistant which can potentially be used by visually impaired people to cross roads in real time. Existing datasets of Indian roads are for semantic segmentation and object detection only. Also, they are not recorded from pedestrian viewpoint and neither are they labeled for road crossing safety. Hence, I introduce INDRA, Indian Dataset for Road Crossing, which consists of 104 videos and a total of more than 26,000 frames. The videos capture various traffic patterns of different locations and times from Anand, Gujarat. I had collected the videos using head-mounted action camera as shown on the slide here. I had also manually annotated the videos with timestamps for durations saved for crossing. Additionally, as an auxiliary data, I release vehicle bounding boxes detected by RetinaNet detection model. Moving on to the model training phase, to start with, the goal is to predict if a given frame is safe or not, given the road crossing labels of past K frames. To evaluate the models, I use precision and recall scores. Elaborating, it is extremely important to have a high precision score as the safety of the user depends on a low number of false positives. Also, while high recall score is not a foremost priority of this application, it's important to have a decent enough recall value because in greed of getting a high precision score, we do not want our model to predict every frame as unsafe. To start with the model training phase, I trained support vector machines on handcrafted features extracted from video frames of INDRA. In the single frame SVM method, I trained SVM on per frame features capturing number, location, size, speed, and direction of vehicles to get precision of 0.68 and recall of 0.87 on the test split. As an extension of this method, I extracted multi-frame features in a sliding window-based manner, and an SVM trained on it gave a precision of 0.79 and a recall of 0.84 on the test split of INDRA. You can find the exact details about feature extraction logic and model training in my paper, but since these methods did not give a good enough performance, and since the feature extraction was too slow to give inference with low latency, I switched to more advanced deep learning methods. While I performed quite a few deep learning experiments, the details of which you can find in my paper, here I present my best performing classifier, dilated road cross net. As shown in the slide, it is a convolutional neural network architecture. Similar to the trend in many neural networks, here I increased the number of filters and decreased the filter size while going deeper in the network. I used multiple batch norm layers and dropout layers to speed up training and prevent overfitting. Also, I had used dilated convolutions to increase the receptive field. On training the model for 150 epochs, minimizing binary cross-entropy loss, I was able to get a precision of 0.9 and a recall of 0.77 on the test split. Since this model gave a high precision score along with a decent enough recall value, I deployed it on NVIDIA Jetson to develop the working prototype of a variable road crossing assistant. I used NVIDIA Jetson Nano and few other supporting components like power bank, headphones, camera to develop a portable road crossing assistant. Since low cost is essential for large-scale impact in India, I chose to work with a separate camera and mobile computer rather than developing a smartphone app. Smartphones with the required deep learning inference hardware are currently way more expensive than my discrete combination of components. The workflow of my prototype is pretty simple, as shown on the slide here. The deployed model on NVIDIA Jetson gives predictions on real-time video stream obtained from head-mounted camera and notifies the user via audio output whenever it is safe to cross the road. Note that I had converted my pre-trained model into a TensorRT model to optimize the processing power and achieve high throughput on NVIDIA Jetson. Here is a demo video of the same. Concluding, I think that this work can prove out to be a useful baseline for upcoming research in this area. I also believe that adding more diversity to this dataset and using spatial temporal features can give us more reliable prediction models. A special thanks to the organizers for giving me this opportunity and for letting me present my work virtually since I could not be there in person. Thank you.